Good morning, everyone. Welcome. Have you ever wondered how your favorite apps can handle just massive amounts of information so seamlessly? Well, it all comes down to database systems. They're the invisible architects that bring order to our entire digital world. So here's our game plan for today. We're going to start by looking at the pure chaos of disorganized data, and then we'll see how a database management system, or DBMS, brings in some serious order. We'll talk about how to design a blueprint for our data, organize it into nice, neat tables, and even learn how to speak to the database to get exactly the answers we need. All right, let's jump right in. To really get why databases are so important, we first have to understand the problem they were built to solve. Okay, so picture this. You're trying to manage all of the university's data in just one simple text file. Every single time a student takes a class, you have to type out their full name, the course title, the professor's name, again and again and again. This isn't just a pain. It's a classic problem we call data redundancy. And this redundancy, well, it creates total chaos. Let's say a student moves. What do? You have to manually hunt down every single line where their name appears and update their address. And if you miss just one, you've created an even bigger problem: data inconsistency. Now your system is literally telling you two different things at once, and you can't trust any of it. It's a complete nightmare to manage. So that whole messy text file approach, clearly a non-starter. And that chaos is precisely why we need a better system, which brings us to our first really big concept, the Database Management System, or DBMS. So what is a DBMS? Think of it like a super organized, expert librarian for all your data. It's a piece of software that sits between you and the actual data files. Instead of you digging through a mess, the DBMS gives you a controlled, structured way to find and manage information. It does all the heavy lifting for you. And here's how it works its magic. First, it tackles that redundancy problem head-on by making sure each piece of information, like a student's name, is only stored in one single place. It also acts as a security guard, controlling who gets to see or change things. Plus, it enforces rules to keep the data accurate, and it protects the whole system from crashes. It's basically a comprehensive guardian for your data. Okay, so a DBMS brings order, but how? How does it actually organize everything? Well, it's a lot like building a house, actually. You have to start with a solid blueprint. In the database world, we call that blueprint a conceptual data model. It's just a high-level plan for what data we need to store, and the most common tool for the job, the one you'll see everywhere, is called the Entity Relationship Model, or ER model for short. Now, the ER model is great because it makes us think about our data in three really simple parts. First, you've got your entities, which are just the main things you want to store info about, like students or courses. Then you've got attributes, which are the details that describe those things, like a student's name. And finally, you have relationships, which is just how these different things connect to each other. And when you draw all this out, you get something called an ER diagram. It's a visual blueprint that makes the whole plan crystal clear. You can see right here our student entity and our course entity are linked together by an enrolled-in relationship. This simple diagram is our roadmap. All right, blueprint in hand, it's time to start building. We're going to translate that ER diagram into the most widely used database structure out there, the relational model. And the translation from our blueprint is super intuitive. It works like this. Each of those entities we identified, like student, that becomes its very own table. Each attribute we defined, like a student's name, that becomes a column in the table. And each specific person or thing, like John Smith himself, becomes a single row of data. And just look at the result. We now have these beautiful, clean, separate tables for students and for courses. Notice how there's no repeated information. John Smith's name only shows up once. But hang on, there's a big question here, right? How do we actually connect a student in one table to a course in the other? The first piece of the puzzle is something called a primary key. Its job is to uniquely identify every single row. So you can think of an attribute like a student ID. It's guaranteed to be unique for each student. It's like a unique fingerprint for your data, making sure you can always pinpoint one specific record. And if the primary key is the fingerprint, then the foreign key is the magic glue that holds our whole database together. A foreign key is just a column in one table that holds the primary key from another table. This creates a reference, a direct link, connecting a student to a course and perfectly capturing that enrolled-in relationship from our blueprint. What this system of keys lets the DBMS do is pretty amazing. It's called enforcing referential integrity. All that means is the database checks the links for you. If you try to enroll a student in a course ID that doesn't actually exist in the course table, the DBMS just rejects it. It automatically stops you from making data entry errors. It's like having a built-in fact checker. Okay, our house is built, the data is perfectly structured, it's safe, it's all connected. Now what? How do we actually talk to it and ask it questions? For that, we use a special language called SQL. So let's say we have a question for our database. We call this a query. For example, maybe we want a list of all the students who are majoring in computer science. The way we ask that question is with SQL, which stands for Structured Query Language. And you'll see, it's almost like writing a sentence in English. We simply select the column we want, in this case, SName, from the table where it lives, the student table, where a certain condition is true, like the major being computer science. And boom, just like that, the database goes and efficiently finds and returns exactly what we asked for. No extra data, no messy files to dig through, just a clean, precise answer that it pulled from our wonderfully structured tables. So let's just take a quick step back and appreciate the journey we've been on here, from that messy file to this really powerful and elegant system. Remember where we started with that chaotic, redundant, totally inconsistent data in a single file? Then we brought in the DBMS to provide control and structure. We used the ER model as our blueprint, then the relational model to build organized tables with keys. And finally, SQL gave us a powerful language to talk to it all. This whole deliberate process, that's the secret sauce that powers nearly every modern application we use every single day. This foundation is incredibly powerful, and honestly, it's served us well for decades. But it does leave us with a final, really big question for the future. In a world that's overflowing with social media posts, videos, and complex AI models, is a world of neat little tables still enough? And that is a topic for another day.